Good morning. It is Saturday morning, the 8th of August at 10 a.m. So it's time for our physics tutorial for this GCSE summer school. Just check that my microphone's on. Yeah, it looks like it's on. Busy week. Lovely weather as well. Okay, so Isaac Physics website has changed. You may have noticed it if you've been logging on and using it. It works the same way, but the design looks slightly different. So I'll show you briefly how that is. This week was about energy, so we'll go through a few of the energy questions, although it didn't look like it caused that many problems, this topic, which is good. And then I'm here to answer any questions that you have or want to go through. And then after that, I will record the video for week 4. I've forgotten what the topic is for week 4 already. Look it up. Had it in my head and I've forgotten it. Topic for week 4 is waves and optics. Well, that's a good one. Got lenses and things in it. So I'll record a video about waves and optics, and then you can get that done over the next week. Just a reminder though, this is a live video, this is a live tutorial, and there's 2 ways that you can interact with me live. One is through Facebook Messenger, and I get those messages through to my phone so I can look at them as they happen. The second way is via YouTube's chat feature. And so if you go to YouTube, and let's just click here it is. If you go to YouTube, you'll see the chat feature, the little chat window on the right hand side over here, where you can type your messages. So I'll say something like hello world, there we go, and then that message would come through. So if you want to send me a message, that's how you can do it. Let me know that you're here watching, or ask any questions you've got as and when you have them. That's the best way to go ahead and do that. And I keep that screen open on the right hand side all the way through this live tutorial so I can see what I'm doing. Just to make sure I can see that nicely. There we go. That looks like that will work. Okay. So this week's questions were from this board here, energy. And you can see the design of the board has changed slightly since I recorded the last video. For example, now we don't have as many hexagons, although I have it on good authority that those hexagons will be returning. So don't worry, I know the hexagons are beloved by students and teachers alike. They will be returning, but right now we are without as many hexagons. But the way the Isaac Physics website works is exactly the same way. So you click a question, it would load up the question, you would then see the question, type your answer, choose your unit, click check my answer, and then the usual hints are there. You've got your notes so that if you're not quite sure what the topic is, you can read something about it. And you've got your hint 2 here, a lovely video going through some of the basics about kinetic energy, but it doesn't specifically focus on that question. That's what I'm doing here today. So the way the website works is the same. It just looks different. So let's get cracking then. If you're out there and you're watching, that's good. Question 1 and 2 didn't cause as many problems at all. A few people tried the first few questions, but then didn't do the last few questions. So I wonder whether they need more focus on the last few. But let's just rattle through these quickly. Kinetic energy at 30 miles an hour sounds difficult because we're not used to miles per hour, but fortunately the conversion's been done for us. So 800 kilogram car and 13.4 meters per second. We'll take a screenshot of this so that I can doodle on it from my OneNote. There it is. And so we know that kinetic energy, E, we'll put a subscript K, is going to be equal to 1/2 multiplied by the mass, which is 800 kilograms, multiplied by the square of the speed, which is 13.4 squared. We'll take out our calculators. 13.4, where's my squared button gone? There it is. Squared multiplied by 800 divided by 2, and we get, is that right? I'll do it one more time because I might have missed a keystroke. 800 divided by 2, yes it is right. So 71,820 odd. So we need to round that, but I'll write that down first. 7.182 times 10 to the 4, and the unit will be joules. Now we need to choose the number of significant figures. So if we look at the data, this number here is 3 significant figures, this number here is 3 significant figures, and so we give our answer to 3 significant figures. 3 significant figures rounds to 7.18 times 10 to the 4. So we go back to the Isaac Physics website, we type in 7.18 times 10 to the 4, and you can do that in a few ways. I'm typing E4 for times 10 to the power of. That's the easiest way to do it. Then click on joules, cross our fingers, correct. That's good news. And then kinetic energy at 40 miles per hour. So we do the same thing now with a different speed. So 17.9 squared, 800 times 2 divide, and that gives us, wow, whole order of magnitude bigger almost. 1.28 E5 units joules, correct. So it's just exactly the same formula as last time, but new numbers. And the last question says, road safety campaigners are continually reminding motorists that 40 miles an hour is much more dangerous. What does this suggest about the issue? And then there's all sorts of nonsense like actually it's safer. What on earth is that all about? No, the kinetic energy is a lot greater. It's a lot more kinetic energy. Just that small increase in speed, much more dangerous, because when you stop, you've got to dissipate that energy somehow. The main way of doing that is to convert kinetic energy into heat. Okay, so let's go back to our previous board. That question's been done. Now, the way I designed this board is the first few questions were just exploring the basic equations for energy that you need to remember, so it was quite straightforward. Here we've got gravitational potential energy, and of course there's a number missing here, isn't there? Which is the gravitational field strength, deliberately missing. So let's scroll down a bit further. Oopsie, that's a bit too far. There we go. So on this question, we've got gravitational potential energy. The equation for that is mgh. So we'll use this subscript, m multiplied by g multiplied by h, which is 500 kilograms multiplied by, we're using 9.8 newtons per kilogram in the Isaac Physics board, multiplied by height. It's winched up 15 meters. And now we can get our calculator out. 500, enter 9.8 times 15 times, and that gives us 73,500-ish. I say ish. 73,500. So we'll put that in standard form. How many significant figures? 2 significant figures this time, because we've got 15 meters is 2 significant figures. So that's 7.4 it rounds to. So I will write that down, the working here, so that you can follow it. This comes to 7.35 times 10 to the 4, but because this number here is given to 2 significant figures, we have to round this number here to 2 significant figures. And if we just write 7.3 times 10 to the 4, that is called truncating. It's not the same thing. I'm just going to check that, yeah, that is right. That's exactly 73500. So we need to round that to 7.4 times 10 to the 4. And type in, that's going to be in joules because it's after energy. Check my answer, correct. That's good news. No one said any questions yet, so it looks like no one wants to interact with me at the moment. I know one of you that usually watches is out camping, so it might be difficult to watch this while you're out camping, but I know there are other people out there as well, so please do join in. Speed after drop. Okay, this is a pretty standard question now. Let's get all this on one screen. This is a pretty standard question at GCSE level, and if you can answer questions like this, then really any of the energy questions that you get, and this sort of question will come up, you'll be able to do with some confidence. So let's give myself a bit more room. We've calculated already the gravitational potential energy. There it is. And then it says, assuming that all of this gravitational potential energy is turned into kinetic energy. Now that wording is the sort of thing you'll find in some textbooks. It's the idea of energy types being transformed. whereas exam boards nowadays prefer to talk about transfer of energy from one store to another. So another way of saying this would be assuming all of this gravitational potential energy is transferred to the kinetic energy store, and that might be a better way of wording it for how GCSEs are asked nowadays. It says work out the speed as it hits the school bus. What on earth is this question about? A pumpkin being dropped on? Oh, okay. So let's do the calculation then. E, which is our kinetic energy, is going to be half mv squared. We want v, so we need to rearrange this. So v is going to be 2 lots of the kinetic energy divided by the mass, all under the square root. Don't forget that square root. Common mistake for students to make. Then we plug our numbers in, so square root of 2 times this number. Now, we're not just going to write 7.4 because we know that that's rounded. We're going to use 7.35 because that's what we actually calculated it to be, times 10 to the 4. That was the kinetic energy, the gravitational potential energy, which will all be transferred into kinetic energy. And then divide that by the mass, which is 500 kilograms. So that was an important point. In the previous question, you calculated the gravitational potential energy to be 7.35 times 10 to the 4 joules. And now we've got a subsequent calculation in which we have to use that previous number. Yes, you've rounded that number to give an answer, but that number that you didn't round is the one you use in the next calculation. That's something you must remember. Now, hopefully the Isaac Physics website is going to get this right. It's usually pretty good at this sort of thing. So we take out our calculator. We've got that energy we had before. We multiply it by 2, divided by 500, and take the square root of it. And we get 17.15 meters per second. I wonder whether it would matter if we use the rounded number. Let's try it and see what it comes out as. So 7.4 times 10 to the 4, multiplied by 2, divide by 500, and then take the square root. Yes, so on the third significant figure it gives us a difference, but given that we are rounding our number, well, even if we rounded the number to 2 significant figures or 3 significant figures, in this case actually it wouldn't matter. Just double check. I say that actually I think it would matter if you rounded it to 3 significant figures, but we're not. As we're rounding this to 2 significant figures, it doesn't matter whether we use the rounded or unrounded. I've made a big deal out of it. Actually, it doesn't matter in this particular question, but in some of these questions it does. And I have had students in my classroom getting quite grumpy that they can't get the answer right, even though they're doing everything right, and it's because they're using a rounded answer from a previous part of the question in the next part of the question. So what was it? 17 meters per second. So that's rounded to 2 significant figures. Take the Isaac Physics website, type in 17, and we cross our fingers and hope that it all works. Give ourselves a bit more room. Meters per second, correct, good. And then we're told, what about 5 kilogram pumpkin? Would the speed be any different? Now, your instinct may make you think, yes, it's a heavier pumpkin, it'll be faster. But have a look at the equations. What you've actually done is this. You've gone gravitational potential energy, which is m times g times h, and you're equating it to kinetic energy, which is a half times m times v squared. And what you'll notice is that the mass of the pumpkin is on the left-hand side and the right-hand side, so you can divide through by the mass of the pumpkin. Doesn't matter. The mass of the pumpkin is irrelevant. The mass of the pumpkin does not determine the speed. It is cancelled out. It is not part of that equation. So you can say, no, it's the same, it doesn't matter. Now, actually, in reality, it will matter, and the reason why it will matter is because if you have 2 identical shape pumpkins, but one of them has a larger mass, then because it has more weight, it has to be going faster for the air resistance to equal its weight. In this question, we're assuming there's no air resistance. We know that because we're assuming all of the gravitational potential energy is transferred to the kinetic energy store. But in reality, that's not what happens. As the pumpkin moves through the air resistance is going to cause energy to be dissipated as heat. And as the pumpkin is moving faster, it will dissipate more energy as heat. So in reality, what happens is a heavier pumpkin will hit the ground faster. That is what will actually happen, but not in the restricted context of this question, where we are told right at the beginning, or right here I think it was, assuming all of the gravitational potential energy is turned into kinetic energy. With that restriction on the question, so there's no energy dissipated as thermal energy, we know that there's no air resistance, and therefore the two pumpkins would hit the ground at the same time. They'd be travelling at the same speed. This is the old, is it called a guinea and a feather, or a hammer and a feather experiment? If you take a hammer and a feather onto the moon where there's no air, so there's no air resistance, and drop them, they'll hit the ground at the same time and travelling at the same speed when they hit the ground. Okay, so that's 34.4 done. Then we move into elastic potential energy. So again, we're just exploring these energy equations. Calculate the elastic potential energy when that much force it stretches a spring by that much. Now you may initially think to yourself, okay, so force multiplied by displacement, that's work done, so all I need to do is multiply these numbers together. But that's not quite true. The reason why that's not quite true is because the more force you apply to your spring, the more it extends. Force and extension are directly proportional. In other words, force is a function of displacement. And so because force is a function of displacement, we can't just multiply those two numbers together. Now, if you want to know more about that, study A-level physics. And if you study A-level physics, we'll talk about force as a function of displacement multiplied by small intervals of displacement and added over all of those small intervals. We'll talk about, that's work done, we'll talk about some calculus, but we're not doing A-level physics right now, so we can keep it simple, and we can say that the elastic potential energy is half multiplied by the spring constant multiplied by the extension squared. You see, the problem here is we don't know what the spring constant is, but we do know an equation that relates force to extension, and the spring constant, K, is the constant of proportionality between force and extension. So rearranging that equation, the spring constant is going to be the force divided by the extension, which we know is going to be 40 newtons divided by, now, half a centimetre, but we're going to want this in meters, really, so that we can get a final answer, the potential energy in joules. So let's do everything in meters. So half a centimetre would be 5 multiplied by 10 to the negative 3 meters. Have I enough room on the edge? No, I'll just write it underneath. So 40 divided by 5e3 minus is 8,000. So 8, and that should be 8.0 or 8.00, 8.0, but I'm just going to write 8 times 10 to the 3, and the units are going to be newtons per metre in this case. So now we've got our spring constant, we can now plug that number into our equation, donk, there. So this equation becomes, don't do your working like this, I shouldn't have done that sloppy arrow. You don't need this arrow, it just looks confusing for the examiner. You don't need to do that. So let's delete that because it's bad practice. So now we'll type it right here now, half multiplied by 8 times 10 to the 3, that's the spring constant, multiplied by, and it was 5 times 10 to the negative 3, and this is all squared, just that bit there. And then we can get our answer. Right, yes, so calculator comes out. And we're going to do 5e3 minus, square that, and then type 8e3 multiply, and 2 divide, and that gives us 0.1 joules, very little energy. 0.1. Well, we need the right number of significant figures. These are two significant figure numbers that we've used in our calculation, so we'll give this a 0.10 joules. And let's hope that that's going to work. Good news. So there's the elastic potential energy one. Then we move into some thermal physics, I think. Is it? Oh, no, we use into power first. We do thermal physics at the end. So power is if energy divided by time. what do we know? We've got a rower exercises the power of this, a boat's going to, how far will a boat go? The first question's got nothing to do with energy, it's just distance, speed, time. So if we're going at 9 meters per second, 20 seconds of 9 meters per second will be 9 multiplied by 20. We'll have gone 180 meters. I'm not going to write that working down because the focus of this is supposed to be on energy, so let's just write down, if I can, 180 meters. There we go. And then, okay, energy. How much energy will the crew have converted in 20 seconds? Just check and see if any messages. No messages come through yet. How much energy will the crew have converted in 20 seconds? So we know how far we've gone, and we know how much... sorry, not far, we don't need that. We know how much power we've got, and we know how much time. So power and time. So let's scroll down a teeny bit. Can we scroll? Oh, let me scroll. Let's scroll down like this. Okay, so power is energy divided by time, energy transferred divided by time. We are asked in the question how much energy the crew will have dissipated, so that's, or converted, that's P multiplied by T. Power was, in the question, forgotten, 200 watts, so write that down, 200, and the time was 20 seconds. And the answer for that, let's just make sure I've got this, 20 seconds, yeah. The answer for that, 200 multiplied by 20, what am I using a calculator for that? 4,000. So let's write that down. That's 4,000 joules, make sure you know the unit. What's nice about Isaac Physics is it forces you to think about not just the number of significant figures, but also the units, because they're so important for physicists. Okay, incorrect. What have I done wrong there? 200 watts. Ah, 7. There are 7 rowers. Fool, you didn't read the question properly. That's embarrassing. 7 rowers. So if each rower is dissipating 4,000 or converting 4,000 joules, then 7 of those is going to be 28000. Is that right? 1, 2, 3, 4. Yep, joules. Count again the number of rowers. 7 other equally strong. Oh my goodness, I really am not reading this question correctly at all, am I? So 200 multiplied by 20 multiplied by 8. There are 8 rowers in total. Oh, I'm doing exactly what the students do. E4, okay. 3.2, E4. And there we go. Okay, so what have we learned from that debacle? Read the question carefully. A rower exercises with that. A boat containing 7 other equally strong rowers. It's all there. It's in the question. I just didn't read it. I didn't read the question. And may God have mercy on my soul. I moan at students all the time for that. Okay, force. Let's move on. Calculate the force each rower this time exerts to push the boat along. So what do we know? We know that force is multiplied by displacement to get the work done. And we know the work done for each of the rowers, because that was our 200 multiplied by 20. That was our 4,000 joules. So let's do some working. Let's write it down. Work done is force multiplied by displacement. Remember, S is displacement. We want to know the work done. What is it we want to know? Can't even remember what we want to know. The force each rower exerts to push the boat along. So we want to know what the force is. So force is going to be work done divided by the displacement. The work done by each rower is 4,000 joules, and they have travelled a distance of, I think I've just accidentally opened something. We've travelled a distance of, yes, I did accidentally open something, 180 metres. Type that down here, 180 meters, so 4,000 divided by 180 is going to be 22.2 newtons. It's a force, so it's in newtons. Let's write this down. 22.2. How many significant figures are we going to give our answer to? Let's just check. So 22.2. That's 2 significant figures, that's 2 significant figures, that's 3, but that's 2. So it's 2 significant figures is the answer we're going to give. So 22 newtons, correct. And then lastly, it says what happens if you multiply the force in C by the speed. So force times speed. So what you're supposed to do through this question is figure out an equation for power, which equals force multiplied by speed. So you get the power of one rower. But is it the force in C? Let's just check that. That's for one rower. And the speed of the whole boat, yeah. So you've derived that equation there through doing these questions. Okay, let's move away from that now. So that's power, done. There's only 3 questions left. We might as well carry on with them. This one here, so we're moving to thermal physics now. What's the change in thermal energy of that much water raised to that temperature to its boiling point? Assume the system is well insulated, and we've got that. Pretty standard question, might be worth 3 marks in an exam. It's not too tricky. So the equation, which you don't have to remember this equation, you're actually given this equation in the exams. Very generous, but you have to know you're given it to know to look for it, which is that the energy which is transferred, or change in thermal energy, is going to equal to the mass of the substance multiplied by the specific heat capacity of the substance multiplied by the change in temperature of the substance. Mass is 1 kilogram. Specific heat capacity is it's water, so it's 4,200 joules per kilogram per degree Celsius. And from 80 to the boiling point. Well, the boiling point is 100 degrees Celsius. So that's a difference in temperature of 80 degrees Celsius. 100 minus 20 is 80 degrees Celsius. Take your calculator out and do 4200. I'm not going to multiply it by 1. There's no point. And we get, let's write it in standard form, 3.36 times 10 to the 5. And the unit is joules. Now let's check our significant figures. This is a 4 significant figure number. This is 3 significant figures. This is 3 significant figures. So the lowest number of significant figures is 3. So we have to round this to 3 significant figures, which, there we are. I've already written it rounded to 3 significant figures. So 3.36 times 10 to the 4, 10 to the 5 in joules. So 3.36 E5 and joules. Correct. Excellent. Next we've got last 2, so this one's about thermal energy as well. Same sort of thing now, but we've got ice instead. Specific heat capacity of ice, there it is. We've got a block of ice removed from the freezer at a temperature of that, placed in the fridge at a temperature of that. After a few hours the ice is warmed up to fridge temperature. Now the ice doesn't change state in this, it's still ice. So it's the same thing we did last time. The change in temperature now is 18 degrees Celsius multiplied by the specific heat capacity, which is 2100, multiplied by the mass, which is 1.8. There's no other trick to this. So that gives you 6.8, and these are 2 significant figures, so 6.8 times 10 to the power of 4, and the unit is joules. Correct. And lastly, 31.9, looking at change of state. There's 2 questions about change of state here. Let's just take a screenshot of this so we can doodle on it. This thing needs to move out of the way so I can scroll down. It's not moving out of the way. There it is, moved out of the way now. So let's scroll down a bit. Okay, so we've got a heater. It's got a power of the heater. Have we got a time anywhere? Yes, we've got a time. So before I do anything else, I know that I'm going to have to know an amount of energy. If I've got a power and a time and we're doing things in energy, I need to know that energy. So the amount of energy that is transferred is going to be the power multiplied by the time, which is going to be equal to 1000 multiplied by, now it's not multiplied by 5 because that's minutes, it's multiplied by 5 times 60 because that's getting my time in seconds. We'll take out our calculator. Does that fit on that screen? Just about. So we take out our calculator and we do 1000 multiplied, type it correctly, 1000 multiplied by 5 multiplied by 60, and that gives us 3 times 10 to the 5 joules. Is that going to fit there? Yeah, you can see that under my head. 3 times 10 to the 5 joules. Now, what's the question actually asking for? It then says, an insulated beaker containing that much water at that temperature, the water vapour is allowed to escape. Assume there's no heat loss to the surroundings via conduction, convection or radiation. So all we're doing is evaporating the water. Specific latent heat of vaporization of water is that. Check the units for that. It's kilojoules per kilogram. So we need to be careful with that. We know that the energy that is transferred is going to equal the mass that is changing state multiplied by the specific latent heat of vaporization. And that's what we've been given. So if we want to know how much water evaporates first, that's going to be the energy that is transferred divided by the specific latent heat of vaporization. The energy transferred, we've calculated. That's the power of the heater multiplied by the time the heater was running for. Then divide that by the specific latent heat of vaporization, but be careful, we want to use joules and kilograms. So this is 2260000, or 10 to the power of 3, times 10 to the power of 3. So we get that in units of joules per kilogram. Plug our numbers in, and we get the mass that is evaporated, but that's not the answer. Not very much mass either, but that's not the answer. So the mass that's evaporated is going to be 0.1327, I'll write it to 4 significant figures, kilograms. Okay, so that's going to be 132.7 grams. And why have I put it in grams? Because we've got 750 grams of that water initially. And the question is how much water is left after 5 minutes. So that's when we're going to do 750 minus 132.7. And the reason why I kept this number here to 4 significant figures rather than rounding it is because it's not the final answer. So I keep 1 or 2 extra digits. We call them guard digits. In this case it's 1 extra digit. This is a 3 significant figure number. Let's change my colour of pen. This is a 3 significant figure number. This is a 3 significant figure number. So I'm going to be rounding my number to 3 significant figures at the end. So I kept this number to 4 significant figures so that if there are any rounding errors, they'll accumulate on that last digit, which I'm going to round away anyway, so it doesn't matter. So let's subtract that 132.7 grams from the original 750 grams, and I get 700 and I've done something wrong. Let's subtract 132.7 away from 750, and I get 617.3 grams, which I can round to 617 grams. That's how much water is left after 5 minutes. So going to here, 617 grams. Correct. And then half evaporated. How long will it take for half of the water to have evaporated? Give your answer to the nearest second. Okay, so I'm just going to erase all this so I can start again with what I need. Let's get rid of all that, all that, all that. Let's get rid of all that, and let's get rid of all this. Right, so now we've got the data we need. We now want half of the water to evaporate. So we're going to have to work in reverse. We want to know how much energy has to be transferred to evaporate half of that. So half of that is 300 and, oh hang on, it's 750. Yeah, 375 grams. So that's going to be 375 grams. Be careful, it's grams, so times 10 to the negative 3 kilograms. Multiplied by the specific latent heat of specific latent heat of vaporization of the water, which was 2260 joules per kilogram, so that's 10 to the 3. And you'll see the 10 to the negative 3 and the 10 to the 3 actually cancel. And now I take my calculator out and go 375, 2260, and that means I've got to transfer 8.475 times 10 to the 5 joules. 8.475 times 10 to the 5 joules. And the question is how long it will take. How long it will take for half of the water to have evaporated. So now we need something to do with time. We know that power is energy that's transferred, which we've now calculated, divided by time. And so the time it will take will be the energy transferred divided by the power, which is 8.475 times 10 to the 5 divided by the power of the heater, which is 1000 watts. And that'll give us the time in seconds. So we don't really need a calculator for that. That's going to equal 847.5 seconds. So if I take my thing here, it says give your answer to the nearest second. So that's going to be 848 to the nearest second. Really hope we've rounded this right. 848 nearest second, 848. Correct. And there it is, that's the end. Really useful thing to do if you're ever making food in the kitchen. You want to know how long it will take before your pan of water boils away. Just do a quick calculation. All you need to know is the power of your hob. Okay, so that's all of the energy questions. That's how you answer them. Nobody's interacted with me today, which makes me feel a bit sad. This is supposed to be a live interactive tutorial where you can ask questions, or you can say, yeah, I got that, or whatever. There wasn't any of that going on today, which is a real shame. So next week will be all about, I think it was waves and optics, can't remember. I'll record the video today for that, get that uploaded, get the board of questions set, and then you can work on that over the next week. Stay safe, everyone. Do enjoy the sunshine, but please remember to keep doing physics as well. It's important. It's important for two reasons. Firstly, when you get back in September, after such a long break from school, you're going to want to make sure that you're in the strongest position possible. And the second reason, if you're in year 11 going into year 12, is you get your results very, very soon. You might just want to be resitting these exams in the autumn term. It's good to keep this stuff fresh. So let's just keep going through the physics. Okay, well, thank you very much for coming along, for watching this, and I'll see you next